In this video, we're going to be analyzing a situation where a proton is released at rest in an electric field, and we're going to solve for the acceleration, final velocity, and displacement of the proton after 40 nanoseconds. So here's some known variables that we have. The original conditions of the problem give us an electric field of 500 newtons per coulomb. The time that the object or the proton is released for is 40 nanoseconds, which is 40 times 10 to the negative ninth. And if it's a proton, we know a couple things. We know that it's positively charged. We know that it moves in the direction of the electric field. And if it is released from rest, we can assume the initial velocity is 0 meters per second. Now, in addition to those three things, we always know a couple constants for an electron. We know the mass, a proton. The mass of a proton is 1.67 times 10 to the negative 27th kilograms. And we also know the Q value of a proton is 1.6 times 10 to the negative 19th coulomb. So we can also use those in addition to the three that were given in the original problem. All right, so the first thing we're going to do is solve for the acceleration, and then we're going to solve for a couple extra variables as well. So the final things we're going to be solving for are the final velocity of the proton and how far it's moved. So it basically turns into a kinematics problem after we're able to solve for the acceleration. Now, if you're doing an accelerated motion kinematics problem, you're going to be using formulas such as these. And when you use these problems, you have to have three known variables, and then you can solve for a fourth variable that is your unknown. So as of now, we have the initial velocity, we have the time, and we're going to solve for the acceleration first, and that's going to be really helpful because there's an a value in each of the three formulas. Now, if we're solving for an a value, we know that acceleration equals force over mass. And if we're analyzing an electric field question, oftentimes we'll substitute in the formula QE for the force. So if we're looking for the acceleration, what we can do is take the charge of a proton, which we know is 1.6 times 10 to the negative 19th, times the electric field value, 500 newtons per coulomb, and we have another constant, which is the mass of the electron, 1.67 times 10 to the negative 27th kilograms. Now from there, if we plug in those values, we can get our acceleration. That comes out to 4.79 times 10 to the 10th meters per second squared. Now we're looking for the final velocity as one of our final solutions. So we can either use the first formula or the second one. The middle one doesn't have a VF in it. Now it looks like the first one is going to be the most simple formula to use to find our VF because it's already set up for VF. So VF is going to equal 0 meters per second plus our acceleration times our time and then our final velocity is then going to come out to 1,916 meters per second. Now for our final unknown variable, we can go ahead and solve for our delta x. We could use the second or the third formula. I'm going to choose to use the second one because I won't have to do any rearranging. It's already set equal to our delta x. So for this one, why don't we clear a little bit of space right above it? So if we set that up, we have delta x equal to, and we don't need the VI times t because our VI is 0 anyways. And then we have 1/2 times our acceleration times our time squared. And then once we take the product of all these together, we get our final delta x value, which is 3.8 times 10 to the negative fifth meters. So to sum things up, when you're taking a look at a charged particle in an electric field and you're solving for values such as the final velocity, the time, the delta x, you're going to use some kinematic formulas. Oftentimes, you're going to find the acceleration first by using this formula right over here, which is basically a variation of Newton's second law, by taking A equals force over mass, but then substituting out the F for the Q times E. Now, if you have an electron or a proton, you definitely have the Q value because those are known values. And then you're going to take your electric field value, which in this case was 500 newtons per coulomb. And then once you find the acceleration, you pair that up with two other values because you need three known values to plug into any of your accelerated kinematic formulas. And then from there, you can solve for whatever you're looking for. In this case, we solve for VF and a delta X. So I hope that was helpful to you. Thank you for watching and listening.